The law of exponential change with Niyo and Melissa. The derivative of y as it's related to t is equal to a constant times y, where y varies as the amount given and k is a constant. Now you separate the variables, putting y on one side and everything else on the other, because for this equation you want to solve for y. From here, now you take the antiderivative of both sides, where the derivative of dy over y is the ln of y, and k dt, where k stays the same since it's a constant, and dt equals t. You add c for another constant, because that's what you do when you take the antiderivative of an equation. Now to isolate the y and get rid of the ln, you must raise both sides to the e power. So that way you have e raised to the ln of y, and it equals e to the kt plus c. After raising e to each side, you are then left with the absolute value of y equals e to the kt plus c. Now e to the kt plus c can be divided up into e to the kt times e to the c, because when you multiply by adding exponents, you can break it up since they have the same base. Now e to the c equals capital C, because now you have another constant. When you have e to a constant, it just stays at a constant. So now you have the absolute value of y equals ce to the kt, and when you have an absolute value, it turns into plus or minus. So now you're left with y equals plus or minus capital CE to the kt. Now that you have y equals capital CE to the kt, you can translate that c can equal y sub naught. So now you have y equals y sub naught e to the kt. In the law of differential equations, you have 4 different values. You have y, which is your new value, y sub naught, which is your initial value, k, which is the rate, and t, which is equal to time. This way, when you're given problems, you can solve for one using another. If you need to find one of them, as in you need to find k, you have to be given the 3 others. If you need to find the initial, you have to be given the 3 others. You need 3 in order to find 1. Let's start with this first problem. The number of a certain type of bacteria increases continuously at a rate proportional to the number present. If there are 100 present at a certain time and 300 present 5 hours later, how many will there be 10 hours after the initial time? How long does it then take the number of bacteria to double? Alright, let's start off with what we know. We know that the initial value is 100, and then 5 hours later, the number is 300. So y sub naught equals 100. The end value, y, is 300, where t equals 5, and we don't know what k is. So in order to find k, we need to plug it in. So we need to find k. So now we plug everything in. We plug in 300, we plug in 100, and we plug in 5. So now we divide by 100, so that we have e to the 5k on one side. So now we have 3 equals e to the 5k. You take the ln of both sides to get rid of the e, so now you have the ln of 3 equals 5k. So now you divide k by 5, and now you have ln of 3 over 5. That equals our k. So now we're looking at how many will appear after 10 hours. Now that we know k, we can then find an end value, plugging in with the initial that we have. So we don't know what y is. We know that y sub naught equals 100. We now know what k is, and also we're given how longer it will take. You plug in all the numbers into your calculator, and your end value will be y equals 900. So after 10 hours, there will be 900 bacteria present. So now we want to look for how long will it take for the bacteria to double. We start off with our original equation, but since we just want double, we want 2y equals 1y sub naught. So now we plug in 2 equals 1 times e to the ln of 3 divided by 5 times t. You take the ln of both sides. So now the ln of 2 equals the ln of 3 divided by 5 times t. Now to find t, you just divide the ln of 2 by the ln of 3 divided by 5. And your end result, it will take 3.155 hours for the number of bacteria to double. Okay, now let's start with the half-life problem. Carbon-14 dating assumes that the carbon dioxide on Earth today has the same radioactive content as it did centuries ago. If this is true, then the amount of carbon-14 absorbed by a tree that grew several centuries ago should be the same as the amount of carbon-14 absorbed by a tree growing today. A piece of ancient charcoal contains only 15% as much as the radioactive carbon as a piece of modern charcoal. How long ago was the tree burned to make this ancient charcoal? Here's a note. The half-life of carbon-14 is 5,730 years. Now we plug in what we know. We know that we want half of the initial value, so y sub naught has to equal 1, and y has to equal 1/2. And since we're given the time of 5,730 years, for only half the initial to remain, we just need to find k. Let's go find k. So now let's plug in what we know. We know that y equals 1/2, and y sub naught equals 1, so 1/2 equals e to the 5,730 times k. Now to find k, we take the ln of both sides, so the ln of 1/2 equals 5,730 times k. Now to isolate k, we divide the ln of 1/2 by 5,730. Now that we have k, we need to answer the question. For how many years have to pass for 15% of carbon-14 to be left? Now that we have k, we need to find a time for 15% of the original to be left. So we take 0.15, which is 15%, of e times the ln of 1/2 divided by 5,730 times t. You take the ln of both sides, so to get rid of that e, and then you divide by the ln of 1/2 divided by 5,730 to isolate t. Now with t isolated, you just plug it into your calculator and you solve. So now t equals 15,682 years. The end. We hope you enjoyed this presentation, and we hope that it helps you in future problems.